So in this short lecture, I'm just going to go over again assigning oxidation numbers to different parts of a chemical equation or a chemical reaction. You have to remember that when we're looking at redox or oxidation and reduction reactions, we're talking about a gain and loss of electrons by way of one thing giving up electrons or being reduced to something else that is accepting, I just said reduced, I'm sorry, oxidized, giving up, losing, being oxidized to something else that is receiving or taking those electrons, meaning it is reduced. So oxidation is loss, reduction is gain. It's a loss and gain of electrons. If a gain and loss of electrons, or if a transfer of electrons are not occurring, then the reaction has not occurred. We can say that it is no reaction. So if I look at the example down here, what I can see is that example is 2Na plus Cl2. I don't know why my arrow moved, but that arrow should be right here. Yields 2 NaCl. So when I look at this, I can look and see that solid sodium will be assigned an oxidation number of 0 because it's in its free state. It is not bonded to anything. It is overall neutral, meaning not charged, and it is as it occurs naturally in nature. So that goes from 0. And on the product side, it goes to a +1 because it'll take on the oxidation number equal to its charge. And the charge on sodium is +1. We know that because it's in group 1 of the periodic table. Chlorine gas here, that is also in its free state. Naturally, in nature, it exists as a gas in its diatomic form. It is not charged, and it is not involved in a bond. Now, you might look at this and say, well, Ms. Meriwether, Cl2, that's involved in a bond. Yes, that is true. But Cl2 is a diatomic form. Naturally, in nature, it's bonded to itself. So it's considered its free state. So its oxidation number will be assigned as 0. And then in the product side, it's a halogen. So the halogens will take on an oxidation number generally equal to their charge. There are very, very few exceptions. And the charges on halogens are -1. So the sodium is +1, the chloride ion is -1. And overall, those oxidation numbers are equal to the overall charge of sodium chloride, which is 0. +1 and -1 equals 0. So we know that because sodium lost an electron, it went from 0 to +1. That's a loss of negativeness. That is the oxidation half of this redox. Where chlorine gas has gained electrons. And therefore, if it's gained electrons, it is reduced. Remember, the thing that is oxidized is doing the reducing of something else. Therefore, it is the reducing agent. If it is reduced, it is doing the oxidizing of something else, therefore the oxidizing agent. You just got to kind of remember everything here is a little bit back and forth. So let's look at another example. When we're talking about the oxidation state increasing from reactants to products, we're talking about an increase in the oxidation state. Reduction, just like it sounds, a decrease in the oxidation state. That is increasing oxidation state because of the loss of electrons. It is increasing its charge. It is getting less negative. It's losing negativeness. Where reduction is decreasing its overall charge or overall oxidation state by way of gaining negativeness. So if I look at the example here, carbon all by itself in its solid, non-charged, free state has an oxidation number of 0. But in the product side, we know that sulfur is 2-. We know that because it is, in the -2 column, so it'll take on the oxidation number equal to its charge. And there are 2 of them. So -2 times 2 is -4. X plus -4 must equal 0. So the only choice the carbon could be is +4. So it goes from 0 to +4. That is a loss of negativeness, a loss of electrons, 4 of them specifically. Therefore, it's the carbon that is oxidized, and therefore the reducing agent. Sulfur also goes from 0, but then to 2-. Yes, we do know there are 2 of them, but we're only looking at each individual sulfur to see what it does. So sulfur goes from 0 to 2-. That is a gain of 2 electrons. So it has gained electrons and is therefore reduced. Because it is reduced, it is doing the oxidizing of the carbon and the oxidizing agent. So here are the rules again. Free elements in their standard state have an oxidation number equal to 0. The monoatomic ions will have an oxidation state, generally speaking, equal to their charge. Very few exceptions. So a sodium ion +1, its oxidation number will be +1. If we're talking about magnesium, which has a charge of +2, will have an oxidation number equal to +2. Chloride ions, it's a halogen. Halogens, when they become an ion, their charge is -1. Therefore, its oxidation number will be equal to its charge. Now, if a compound is present and there's no overall charge on that compound, then the oxidation numbers need to add up to 0 if it is a neutral compound. If it is overall has a charge, the oxidation numbers must equal whatever that charge is. So in this case, we can mathematically figure out that oxygen and nitrogen, their oxidation numbers, because we know oxygen is 2-. We know there are 3 of them. And that added to whatever nitrogen is, they must add up to equal -1, which is the overall charge on nitrate. So the 3 times 2- must add up to something that equals -1. In this case, the only choice is +5. So the oxidation number for nitrogen is +5. This is what I was talking about when we say nonmetals, generally speaking, will take the oxidation number equal to their charge. And normally nitrogen's charge is 3-, but clearly there are 2 nonmetals there. So one of them has to be positive and the other has to be negative. Because oxygen is much more electronegative than nitrogen, oxygen gets first dibs on the negative oxidation number, and therefore nitrogen must be the positive oxidation number. Okay, another kind of group here, don't know what happened with my numbering. Group 1 metals, all group 1 metals in their oxidation state of +1, because they will take on the charge, whatever their charge is, and for group 1, that's +1. Group 2 metals, again, they will take on an oxidation number equal to their charge, which the group 2 metals have a charge of +2. Fake number 5 here. This is important. In their compounds, nonmetals have oxidation states according to the table on the right. Okay, so the positioning of the nonmetal is important. And so what you see here, you can memorize this, but just know that you can also just do the math. Okay, so the more electronegative, the higher the ability for that element to have the negative oxidation number. So here are just a few examples of assigning oxidation numbers. If we look at Cl2, what we can see is that because Cl2 is a free element in its standard state, just as it appears naturally in nature, its oxidation number will be 0. Remember, Cl2 naturally occurs as a diatom. B is a monoatomic ion. So because it's a monoatomic ion and that it's a group 1 metal, it will take on an oxidation number equal to its charge, which is +1. Kf, if we look at those, potassium is in group 1. Therefore, it'll take on the oxidation number equal to its charge, and group 1 metals have a charge of +1. Therefore, their oxidation number will be +1. And the oxidation state of fluorine is -1. It is not only a halogen, but it is extremely electronegative, and therefore it gets first dibs on the negative oxidation number. And this is an ionic compound, another reason the nonmetal gets the negative oxidation number. But halogens take on the oxidation number equal to their charge, which is for halogens, -1. Carbon dioxide, we know here, oxygen, the only exception to oxygen being 2- is peroxide. You remember H2O2. But oxygen is 2-. There are 2 of them. So we can mathematically figure out that since the whole thing is neutral, the oxidation state for carbon must be +4. Okay, oxygen, even though carbon and oxygen are both nonmetals, oxygen is much more electronegative and gets first dibs on the negative oxidation number. SO4 2-. This is where we have to set all the oxidation numbers of the S and the O equal to -2 because it is overall charged. And therefore, we can just, again, set up a quick algebraic equation. So we don't know what sulfur is. Because we do know what oxygen is, we can figure out sulfur. So we know oxygen is 2- and that there are 4 of them. And that, plus whatever sulfur is, must equal -2 because the entire element or compound is overall charged. So the oxidation numbers must equal that -2. So if you just do the math, if you have x minus 8 equals -2, you can say that S is equal to +6. So the oxidation number for the sulfur in sulfate is +6, and each oxygen is -2. For potassium, again, rule 4 applies where it's in group 1, and therefore it'll take on the oxidation number equal to its charge. And oxygen will be, well, gosh, we don't know. Here's another exception, okay? Not a very common one, but an exception nonetheless. So we don't know what oxygen's going to be. We have to set it up. We know there's 2 potassiums, so it'll take the +1. And we know we're going to look for it this way, because if you just threw a 2- in here and you got 2- times 2 plus 1 times 2, it won't be equal to 0. So in this case, you know the one that you have to try to solve for is the one that's more electronegative, okay? So, and there's a lot of different reasons as to why this exception occurs with here and peroxide. Basically, when you get that O2, H2O2, K2O2, when you get that O2, you're going to have a shift in the oxidation state with oxygen. So we know potassium absolutely 100% will get the +1. There's no other choice it has. Multiply it by 2 plus 2x. The whole thing's got to be equal to 0. So the only way to make that work is to make oxygen's oxidation state be equal to -1. You can try these for practice. The chromium ion, the carbon tetrachloride, the strontium bromide, the sulfite, and nitrate. And pay close attention to, when in doubt, doing the math. Okay? If you have any questions, please let me know. This is the end of this particular short lecture. I'm going to do another one that is balancing and basic solutions. And I'm going to talk a little bit more about what we did today with balancing by half reactions with adding the water. Okay? All right, on to the next one.